Okay, so let's get started. First of all, we're going to review last lecture. Last week we looked at this diagram, right? This is the overview of 8051 or any other microprocessor architecture, and this is an example of 8051. And we learned the memory address space. Remember that? The memory address space. This one basically is not an actual memory, right? This is just a space. This is the address space. And out of this space, which is 64K, 16 bits, right? We have an address of 16 bits. So therefore, the whole space, whole address space is 64K. So out of this 64K, you can use maybe 4K if you like. Okay? This is the address space. This is the address available for you. So if you can, then you can buy a 64K memory and put that in here and use all of that if you want. Or if you want, you can buy only a 4K memory and put that 4K in here so that you want to use only from this the base address to the 4K address. And all the other addresses still it's not used because it's not mapped to actual memory, but you still have a space. Later, if you buy more memory, you can put and use more space. Okay? So this is just space, not actual memory, right? And we have two different types of memories. One is the program or code memory or instruction memory. And second thing is we call this a data memory. You may want to remember the difference. Okay? This is where you put your code. You write your own code and compile and make a binary and put those binary in here. Okay? Maybe download your program to here. So this is where you put your program, and later the microprocessor read one by one and execute line by line. Okay? Whereas this memory is to put your temporary values. If you declare A, B, C, D, for example, those temporary values can go here. Okay? This is for data. Or let's say you want to, when you use a C, right, sometimes you declare some array. You know array? Some series of data, right? Those array or any other kind of big data should go here, right? So this is where you want to put your own value or temporary value or some of the variables. This is internal RAM, and this internal RAM typically goes here, right? Because this is a very special memory where, what is this one? This is called bank, right? Bank consists of registers. We have 8 registers per bank. Each bank we have 8 registers from R0 to R7. This one also have R0 to R7, right? We have 4 of them. And this is another special address, special memory. This is general purpose memory. And this is called the special function registers. And we have, okay, I didn't include it here, but remember that last week we learned this one, right? Pretty much all the registers we see, like accumulator, A, B, or P0, P1, and all those registers, right? PSW, program status word. Those registers are here, okay? So this is designed for special purpose, special function register. So you are not going to do anything with this. If you want to use, let's say you want to calculate A plus B, then those A plus B and those temporary value, you can use this memory if you like. But this memory typically is for special functions like accumulator and those things. Each register has its own dedicated address. Okay? So remember that there are some gray area, right? Unused area. You should not touch those area. Okay, so we learned these things, right? Some registers in 8051 and internal RAM. Also, we learned some families of 8051. Some of the 8051 family have no internal ROM or EPROM or flash. Okay? And here's some characteristic of internal RAM, 4 register banks, and each bank has 8 registers. So therefore we have a 32 general purpose registers. Here you see the 16-bit addressable byte. So now, here's one interesting thing. Let's see. This is where you put your value. And you know each size, each address has 8-bit. Okay? This is a byte address. We call that a byte address because each one is a byte. So 0000, that's a byte. 0001, another byte. So it's like this, right? Remember that we illustrate this one as a town, right? Last week. We have a town, this big town. That's like this address space, right? Okay, so we have this much area. And in this area, let's say we build 100 houses. Okay, all the other area, it's empty still. Okay, so those 100 houses is like you put 4K memory. All the other 64K minus the other 60K, it's like empty right now. Okay, we only have a 4K memory mapped into this address. Now let's see. Each byte has its own address. 0000 is the first byte, and 0001 is the second byte. That somehow is similar to each house has the same size. Each house is like a byte. Okay, this house has 0000. This house has address 0. Next house has address 1, right? Address 2, and each house is like a byte. Okay, that's the size of each address. That's why we call it a byte address, because each one is a byte. Okay, this byte we call it 0000. Next byte 1, next one 2, like this, right? So in other words, size is a byte. Now then, however, if you look at this one, right? This is the address. But address space is 16 bits. Okay, we have 16 bits of address. Okay? So data is 8-bit, but address is 16-bit. Right? Data, actual data goes here, right? Goes inside the memory. Actual data is 8-bit because this is byte. Actual data is 8-bit, but address we have 16 bits. So something like this, right? Again, going back to the illustration, we have a town, but the size of the town is like 16-bit. So we have a big area, big town, like 16 bits. But actual house is like a byte, small house. So many small house. In this particular case, it's like a 64K. 64K is like a 65,535. That many houses, but each house is like a byte. But we have a big area, like 16 bits area. You see that? So this is the address space, 16-bit address. But each one is a byte. Data is byte. So let's go to the next slide. So we see here we have a 16-bit addressable bytes. So we have a 16-bit address. But each data is 8-bit. This explains why we have some registers 8-bit, some other registers 16-bit. Okay, this is why. Here, let's see. We have accumulator and we have a B, and we also have other registers, right? All the registers pretty much are 8-bit size. Because here A and B, typically when you calculate like some addition or something, right? Those value goes into here. So this register A contains your value, data, okay? Data goes into A. So therefore your data typically is 8-bit, so therefore register is 8-bit. But look at here, 16-bit PC and data pointer. These two registers are very special registers that contain address. Okay? This register, you have address. And our address space is 16-bit, so therefore these particular registers has to have a 16-bit size. That's why it's a 16-bit. Okay? Address go into this value. Address goes into these registers. This register, this register. Understand that? Okay. A and B, these registers, you put value into the register. PC and DP, the data pointer, you put address value, address into the register. Okay? That's why we have 16 bits for those two. We'll see that later. Okay, I think we spend a lot of times here, explaining here, right? There's a register called the program status word. This particular register, basically tells you the condition of the processor. So what condition do we have? First of all, carry. Carry is one of the conditions. Auxiliary carry, this is not used. These 2 bits is for bank select, okay? And this one, overflow. And last thing is parity. This one is reserved for later use, so you don't have to you don't care. So what we need to look at here is the 7th, 6th, and 2nd, and the last bit. Okay, those 4 bits we need to know. All the others is pretty straightforward. This is not used. This is not used. This is a bank select. So if you need, then you can put 0, 0 if you want to select the bank 0. So it's just straightforward. But this one, and this one, these 4 bits constantly change whenever you do the calculation. In your program, right, you do like addition, subtraction, multiplication. Whenever you do that, this one just change every time. Okay? Let's say you do this calculation and the result goes to 9 bits. Suddenly this one carry flag is on. Okay? And also the auxiliary carry is on in this case, right? So something like that. If you later you do this calculation and this is the result, overflow flag is on. So this is on all the time. Every time you do this calculation, this flag is on, off, every time. Okay? So generally, why do you need these things? Is because to check the condition. Like, let's say you do this calculation. This goes to A, this goes to B, and you do A plus B, right? And this is the output. This is the output. However, if you don't check carry, okay? If you don't check carry, then maybe you can neglect. The output can go to 9 bits. You know what I'm saying? So whenever you do addition, first thing is you have to check carry. Okay? Because if you don't check carry, then this result may happen, okay? Which is error case, but you can just go ahead. It's not easy to find such kind of bug. That's a bug, right? So for example, right? Let's say you do a for loop. In C language, for example, right? Let's say I start from I equal to 1. I forgot the syntax. Is that correct? Or is it the other way? It's okay, it's the other way, right? Yeah. So I'm trying to increment I from 1 to 70, okay? And what I want to do is that, let's say I want to, let's say my J is 60, and what I want to do is, no, let's say what I want to do is I, let's say J equal to 0, J equal to J plus I. Let's say I want to do this. I mean, just simple program. If you write this way, right? This is C code, by the way, but think about the assembly. It's pretty much assembly, same language. It's another language. So when you do this, right, then what do you expect? As an output, you probably expect like a J on the first loop, J equal to 0. So 0 plus 1, the J becomes 1 on the first loop. On the second loop, J was 1, so 1 plus now I equal to 2, so J equal to 1. Now in the second loop, the output becomes 3. Something like this, right? So now that we have 70 times. So pretty much the end of 70 times, you are expecting j equal to pretty big number. Okay? However, what happened is that since we have only 8-bit value, 8-bit register, right? At some point, maybe, I don't know, maybe some, right now we do a 70 loops, but maybe on 20 or 30 loops, your value is big enough, is bigger than 8 bits, right? At some point now, as you can see, you just keep doing addition. In this program, nothing wrong. There's nothing wrong if you assume that this I, and this actual j, if this j is 32 bits, then this program has nothing wrong. Because j is pretty big container, 32-bit container, so the even big number, no problem, right? But now suppose that j is only 8-bit container. Okay? This j is only small container, but now when you do loops, right, the value becomes big. So definitely this small container cannot hold this value, right? This value is too big. That happens at certain point, but you don't know when that happened. Okay? So therefore, in this case, this kind of program, what do you need to do? Whenever you do addition, you have to check carry. If you don't check carry, then this happens at certain time. You never know when it happened, right? So every time you do addition, somehow you need to check carry. If a carry is 1, suddenly becomes 1, that basically means that this happened. Okay? Then what should happen? What do you need to do? If suddenly carry happens, then at that same moment, the output, okay, the output of the addition becomes small. Okay? Like at some point, j was 2 to the 6 to 7. J was 75, and now our new I was, let's say, 55. So therefore, you do addition, the output, becomes 130. Okay? If this is the example, right? If this happens, now instead of j equal 30, what you have is 2. You basically guess that it should have 130, but instead you're going to have 2, right? Suddenly the value is reduced because the output is bigger than what you can hold. Okay, your container is only this much, but the value is much bigger. So this overflow, this kind of carry happens. So carry flag is on, but the actual output remaining in the container is just 2. So definitely it's an error case. But in this case, you never know. Okay, definitely when you run this one, your output is completely wrong. But look at this code, nothing wrong, right? You don't see anything wrong. However, that's wrong because of this reason. So that's why every time you do this kind of calculation, you need to check carry. Similar reason, if you may want to check the overflow. Okay? So this program status word is to give you such a kind of function. Okay? You want to check. Okay, if I have a carry or if I have overflow, something like this, right? That's the condition you want to check every time you do that kind of calculation. Now let's move to stack. We've really looked at stack, but the main thing is that this stack is a memory, is internal memory. So there is a certain memory called the stack, okay? And this stack basically contains some temporary value. But stack always is like a last input, first output. It's not a regular memory where you read, where you give the address and the memory returns. Generally in memory, right? Any memory, if you want to read, let's say there's a memory here. Then if you want to read this byte, then you give the address, then memory returns the value. If I want to read another address, then simply I give that address, that will be returned, right? That's how you use memory, how you read it, how you write it. But in stack, okay, this is the same memory, by the way, but in stack, how things work is that we have a memory called the stack. Here's a physical memory, and we define that from here to here is stack. We define that. We just declare that from here to here, we call that as a stack. Okay? We call this region as stack. And the bottom address, each one has a byte address, of course. This is a memory. So the bottom address we put as a stack pointer. And how to use a stack is that you don't actually write, you don't access arbitrary memory address. Okay, that's not how you use a stack. How to do a stack is that you put the value one after another on top of it. So think about the container. Again, this whole stack is like some big container like this. Let's say you have a container. Okay, and in the container, let's say you put a magazine. Okay, you put your books. Let's say we have a big box. Stack is like a box, and you want to pack. You want to put your books. Okay. Okay. How things do is that you put the first book you put into the box, then that first book goes to the bottom of the box, right? It never happens that book is up on the air. Book cannot fly, right? So book goes into the bottom of the box. And the second book you put it into the box, that second book will go on top of the first book, right? It's like one on top of another. Later, now you want to bring the book out, okay? You want to put the book out. But let's say here's a box, and we put the first book, book 1, goes in here. And you put the second book here. Let's say you put the 3 books, one after another. Later, now I want to read this book. Okay, second book. What do you need to do? First thing is that you have to bring this out, and then you have to bring, right? You cannot go into this one directly. You first have to bring this one out, this one out. That's what they mean as a last input, first output. What that means is, let's say, think about these 3. This book went into the box first, right? This one go into the box first. And then this one goes into the box, and this one. So this is the first book going to the box. Second one, and this book is the last one. Go into the box, right? This is the last one. However, when you bring the book out, this should be the first one you're going to bring it out, right? That's what they mean. Okay, last input, which is book 3 in this case, will be the first output, which is the same book, right? Or you can say first input, last output, basically same thing. Okay, that's how you use a stack. That's how you use stack. Now you may want to ask a question. Then this is memory, like the same memory, which means that this is like a same memory. So therefore, each byte has its own address. Like this one is like 100. This is the example. 101, 102. Okay, each one has its own address. So this one has its own address, like 101, 100, 101, 102. Okay, because this is regular memory, it's like the same as others. Each one has its own address. So if I want to get this value, right? And I have 3 books here, but if I want to read this value, why not just go there and read it out? Maybe you want to ask a question, right? You can do it if you like. because this is the address, this is the memory, same memory as others, you can do that if you like, but that's not the right way to use a stack. In regular memory, like a data memory, right? You put the temporary value, so that's how you read it, okay? Temporary A is here, B is here, C is here, so if you want to read A, then directly access to A using this address, and also you can access B using the address of B. You can do that, but stack, physically it's the same address, but we declare that this memory is a stack, and for stack, let's use this way, like a last input, first output. Okay? This is the way of using stack. It's not physically different. It's same memory. But we're going to use this way for stack. Okay? We are not going to directly access to a certain memory. What we are going to do is that we just put the memory on one after another, and we bring out one by one. Okay? Like you do push, like a put another book in here, like a book 4, put some value into the stack, that's push. Like a box, right? You have a box, and you push one more book. Push. Okay? Pop is bring the value out. That's pop. This is pop. So this stack, we declare this memory as a stack, and for stack, we agreed, okay? We agreed that for stack, we only use push and pop to access this stack. Okay? For this stack, we are not going to access arbitrary value. We only use push pop to put the value and to bring the value out. Okay? That's a special way of using it. Okay? That's called the stack. So this is an example. As I said here, the last one, the bottom address, is called the stack pointer. It's called the stack pointer because this SP points out the bottom address of stack. Okay? That's why we call it a pointer, stack pointer. Stack pointer is a register. We have this register. And this is an example. Let's say stack pointer says 20H. Then this is address, memory address. And we have a stack pointer 20H right here. Which basically means that right now the bottom of our stack is 20H. Okay, so here's an example. Let's say, again, going to the box. So I have a box called the stack. This is my box, and I call that a stack. And I put book 1. Earlier, this one, the bottom, really the bottom of the box was stack pointer. Now I put the book 1, okay, one value push into the stack. So now this one is stack pointer. So stack pointer basically points to the book 1. Which is actually now the new bottom. This was the bottom because earlier it was empty, but now I have one book. So now this is the bottom. Okay? So stack pointer is pointing this one. Now later I want to push this one in here, right? I want to push new value into the stack. Then this one goes into it. Book 2. Now this becomes bottom, right? Because I put one more book, so this becomes now bottom. So stack pointer should pointing here. Okay? Now my stack pointer is incremented and pointing book 2 because this is the bottom. So that's how. And now let's say later. Now I want to pop this value out, okay? Pop book 2. When I pop this out, right, then this is now gone. So therefore, the stack pointer now has gone back to SP here. Because now this is a new bottom. Okay? So stack pointer always pointing the bottom of the stack. So here in this case, stack pointer is pointing this one. This is like a book 1. Book 1. So whenever you want to push a new value, that new value should go to this one, right? Because this is the, you already have a book 1 here. So new value, which is book 2, should go here. That's exactly this case. So you do push 00H. So 00H basically means that 00H is the same as R0, right? Now we have value AC in R0. So if you run push 00, that basically means that I want to put this value and push it into the stack. That's what that means. So this AC now, which is book 2 in our example, this is like book 2, right? Book 2 goes into here. Okay? And since that goes into here, now my stack pointer is incremented to 21. So this is now my bottom of my stack. Okay? Right? And let's say later I want to do push another one, another value. Okay? Push it one more time. In that case, that new value should go into here, right? And my stack pointer should be incremented to 22. Same way, right? That's how you do it. Every time you do push, the stack pointer is incremented, and new value goes into one on top of another, one by one. That's what happens when you do push. But later, if you want to do pop, okay, pop, you bring the value out. And this value should be out and go into somewhere, right? That is this one. So I do pop 01H. 01H is R1. So this value, since I do pop, right? This value now will go into R1. Okay, so earlier R1 was 00, but now this AC goes to the AC, goes to R1. And R1 becomes AC. And since I pop, what happened is now the book 2, we remove it from the box. So therefore my bottom, the bottom of my box goes down to this one, right? So therefore stack pointer should go down to 20H. Okay? You pop it one more time, then keep going down. Push it, keep going up. Okay, that's how you use stack. Actually, the last Tuesday, right? One of you asked a question, but that was a good question. Now, you may want to ask a question like, we have a book 1 here. Now, I have a book 2 put into the box. And later, I do a pop. So I bring the book 2 out. Then why do we have still this? That's probably the question you may want to ask, right? We still have the same box. I just paint. The red one is something that you want to watch, right? I just, something changed. I change it. I put that in the red one. But I bring the value out, and that value goes into R1. But this value is still there. The reason is that you bring the value out doesn't mean that this value is cleared. Okay? This value does not have to be cleared. It's not reset. Okay? You don't reset it. It doesn't have to be 0. Why? If you want to, let's say you bring this value out and this becomes 0, that means you did it. You make it 0. You have to make it 0. Only then this becomes 0. Otherwise, this value, the memory stays there. Whatever value you have in the memory, it's still there. Until you remove it, until you clear, the value is still there. But since my stack pointer is decreased to 20, this is my bottom of my stack, right? So even though you have this value is considered as garbage. Garbage, okay? Has no meaning in this case. This value definitely has some meaning, like this is really book 2. But in this case, this value has nothing. This is nothing, okay? Looks like the same thing, but this is garbage. You don't have to worry about it. Later, let's say later I do a push again. Okay? So this is bottom now. Let's say I do push and let's say I want to put the value like 0, 1, H. In that case, what happened? In the next step, let's say I do a push and the value 0, 1. Then that 0, 1 will go into here, right? And you're going to override it. So this value will be gone anyway at some point. So right now, this is garbage. So you don't have to worry about it. You don't have to make it 0. It never be 0. Okay? You got the point? Looks like the value is stay there, but you don't have to worry about it. What is important is that this value is now in here. That's the important thing. This value has meaningless, no meaning. Okay? That's a stack. So you need to remember exactly what happened in the stack. This is very important. Okay, so let's see. We have two different architectures in microprocessor. Okay, first of all, first one is a Harvard architecture. Okay, and second thing is called the von Neumann architecture. So let's see what it is. This is general architecture about the microprocessor. Harvard architecture, we have, let's say this is a control unit. We have an arithmetic logic unit, and we have an input-output, right? These three are the basic part of your microprocessor. But every microprocessor, you should have interface with the memory. Right? We learned that you need a data memory, instruction memory. You need so many different memories, and you need to have so many different input-output. Let's say your microprocessor or microcontroller should connect to the LCD button, things like that, right? In order to connect to those kind of devices, you need to have an input-output port, which is this one, right? And since your microprocessor or controller sometimes need to do calculation, you need ALU. Okay, so these three are the basic blocks. But in outside, typically, or it could be inside, but you need a memory, like instruction memory and data memory. And this Harvard architecture is like you have two different buses to connect the two different memory. So what is bus? Like a bus. Okay, simply speaking, bus is like a cable. It's not exactly cable, but it's like this is all happen in the hardware. So inside the hardware, this memory and control unit, these are connected. Okay, the connection, that's a bus. The connection, physical connection. In Harvard architecture, you have two different connections to connect to two different memory. So here is the instruction memory. You compile your own program and put that into the instruction memory, right? And this is the data memory. You have two different connections, independent connections. So therefore, it's like this, right? So this is like a human being. This is a brain. You use your brain to do some calculation, like addition, things like that. I/O is like what? Like hands, right? You connect to LCD, you connect to buttons, things like this. This is like another hands, like this, right? You need to connect to the memory. And this is another memory, so you need to connect to it. So there is two different connections for two different memory. So it's like two different hands. With this hands, you connect to your microprocessor. Using this hand, you connect to the instruction memory. And the other hand, you connect to the data memory. So which means that you can access two different memory at the same time. Okay? You connect to the instruction memory at the same time you connect to the data memory. You do two things at the same time in Harvard architecture. Simply speaking, that's what it is. To do that, as you see here, we have a program memory, data memory. We have two memory separated. Physically, two different memory. And physically, we have two different buses. And each memory has its own address space. Okay? This is a code memory, which is this one. And this one has its own address space of 64K. And data memory has its own address space of 64K. So for example, right, I want to read, let's say 100H in instruction memory, At the same time, I want to bring the value like a 200H from the data memory, right? 200H to the data memory, 100H to the instruction memory. You can do the same thing. Okay? So address space for code memory, data memory, it's independent. You have two different address space. Okay? That's the Harvard architecture. Now, then another architecture is von Neumann architecture. In this architecture, you have only one memory, physically. Physically, in hardware, you have only one memory. Definitely, you have only one bus. You have one connection. So this diagram, right here, control unit, ALU, input-output, these things is microprocessor. Inside the microprocessor, this is a bus. Okay, we have only one bus. And using this bus, it is connected with one memory. Physically, it's just one memory, like this. Therefore, you have only one address space. You have physically, you have one memory, so you have one address space. Out of this 64K of address space, this part, this address space, we use that as a data memory. And the other address space, we use that as a code memory. Okay? That's the von Neumann architecture. It's like this, right? In the Harvard architecture, in the previous architecture, we have two different address space. So it's like a two different town. Okay? Two different town. Right? I can access 100, address 100 in here. At the same time, I can access 200 here. Okay? Same time. However, in this case, we have a one address space because we have a one physical memory. So it's like we have a one town, like just one town. But in one town, we divide it. Okay, this within one town, the left area, it's like a data memory. Okay, the other right area, we use as code memory. Okay, something like that. So in this case, since we have only one bus, you cannot access two at the same time. Okay, you want to read this instruction from code memory, and later you can access here. Okay, one by one. Okay, you cannot access two at the same time. We have only one bus. So difference is that in Harvard architecture, you can access two memory at the same time, so it's maybe faster. Okay, performance. What is performance? Performance basically means that how many instructions you can execute within certain unit time. So how fast? Okay, how fast you can run, that's the performance. So in Harvard architecture, it's faster, right? Because you can access two at the same time. But here in von Neumann architecture, maybe a little bit slower, but this is much easier in hardware, right? You need only one memory, one bus. Okay, this is much easier or simpler. So there's some pros and cons. Okay. Now, very important concept, very, very important in microprocessor. There's a concept called the pipelining. Okay. Maybe, let's say, maybe some of you buy some computer parts like a CPU, video card, and main board one by one and put it together and make your own computer, right? Some of you may do that. Then whenever you buy a CPU, like an Intel processor, probably there's a book inside, like a data sheet or some specification of the book, of the processor. If you read it, I don't think you read it, right? But if you look at inside, then if you read it, then this book will give you the details, or a little bit of details, technical overview, technical specification of the processor. Then you probably see this word, pipelining. So what is pipelining? Pipelining is the technique to execute many instructions per second. The purpose is to run the instructions faster. So here's one thing. First of all, we need to understand these stages, okay? These stages, what that means. To understand that, let's think about a simple diagram. let's say we have instruction memory, and you have all of your code inside the instruction memory. And this memory, instruction memory, is connected to your microprocessor. You know, microprocessor, we write it this way, micro P processor. Okay. Of course, there are other things, but let's simplify the diagram. We simply have instruction memory, microprocessor, and instruction memory, you have your own code. First thing to do is that microprocessor will go there and read out the instruction. Your instruction or your code is in here, right? So microprocessor should go there and bring it, read it. Okay, that's fetch. In English, right? Fetch means bring something out, right? That's fetch. So read the value from the instruction memory. That's fetch. That's the first step. For every instruction, they do fetch first. For every instruction. In instruction memory, right? You have a lot of instructions, right? When you have a C code, you compile it, okay? And it becomes binary. Then those bunch of instructions go into here, and this microprocessor basically go there and read one by one, okay? So for single instruction, I'm talking about one instruction right now. So go there and read out the first instruction. You may have multiple instructions, but microprocessor go there and read the first one out. That's fetch. And once the microprocessor fetch it, then microprocessor should do decode. What is decode? Microprocessor will look at what instruction it is. It is maybe add, or maybe multiplication, or maybe store, right? This guy has to know what it is. Okay? So that's decode. And once this microprocessor look at it and decoded it, then microprocessor has to do execution. What is execution? If this is addition, then you really have to do addition. You need to do it, right? Decode is like, now I see the instruction, oh, this is add. That's decode. Okay? If this is add, then you actually have to do addition. The actual work, that's execution. Okay? That's a third step to do. Once you do execution, for example, addition or multiplication, depending on the instruction, then you will probably have a result, right? When you do addition, then there will be outcome. There will be result. Okay? That output, you have to put it into a certain memory because later you want to use it, right? So that output should go to somewhere. Okay? You store, you save it somewhere because you use it later. Okay? So that process is write back or save. So every instruction, you need these 4 stages. First of all, go there and read it, fetch, and now look at it, what it is, decode, and do execution, third stage, and then the result, you put it into a memory, save. And then go there and read the fetch next instruction, and decode, execute, and save it. And go there and the third instruction, fetch it, decode, things like that, right? Okay? So for every instruction, these 4 stage is the basic. You need to have these 4 instructions for these stages. You need to have these 4 stages for every instruction. Okay? Now, let's understand the pipelining. Since we have 4 different stages, what pipelining does, okay, what pipelining does is like following. Microprocessor go there and fetch the first instruction, okay? And then next thing to do is a decode, right? So this microprocessor fetch it first, and on the next stage, look at this picture. This is clock cycle. So on the first stage, it's already gone to like this. But on the first stage, let's say there's nothing here. I mean, let's not say nothing. The first instruction will go into the fetch on the 0th cycle. Okay? On the next cycle, the first instruction now goes into decode. Okay? Since I fetch the first instruction, on the next clock cycle, I'm going to decode the first instruction. When you decode the first instruction, at the same time, you can fetch the next instruction. So it's like you are very busy. You fetch the first instruction, and you decode, and same time you fetch the second instruction. Okay? And what is the next one? Once you decode, then you have to execute, right? The first instruction probably go to the execute. Then at the same time, second instruction was fetched. So now it goes to decode. Okay? Since the second instruction goes to decode, now you can fetch the third one. So at clock cycle 0, you fetch the first instruction. On the next cycle, first instruction now go to the decode, and second instruction go into fetch. Okay? So the first instruction is here, second instruction is here. On the next cycle, first instruction goes to execute, second instruction goes to decode. Now the third instruction go into fetch. Okay? On the next cycle, first instruction go to this one, second instruction go here, third instruction go to decode. Now the fourth instruction go to fetch. Okay? One more cycle later, first instruction, it's all done. So it's out. And second instruction go here, third one goes here, fourth one goes here, now fifth instruction goes into here. Okay? That's what you see in this picture. Okay? That's what you see. So it's like they actually move one by one after another. Every cycle, every clock cycle, they move. So once you do this, right, it's like a parallel processing. Now let's compare the dumb way. What is the dumb way? Dumb way is that on the one instruction, you fetch it and decode, execute, write back, and finish. And then go to instruction memory, and next to instruction you fetch it, decode, execute, write back, and finish. And then next one. You can do it that way, right? You read one instruction and finish all this, and then fetch the next one, and finish this, right? You can do it that way. However, if you do that, right, then let's say you have a one instruction, fetch, and decode, execute, write back. You need 4 cycles to finish one cycle, one instruction. And after that, now you fetch a new instruction. Again, that new instruction takes 4 cycles. Every instruction, it takes 4. That's a dumb way. Better way is like this. They actually do parallel processing. Once you do this, right, then we have 4 stages. So at certain point, we have 4 instructions inside the stages, right? Maybe on the first instruction are on the write back, second instruction is execute, third instruction decode, fourth instruction are inside the fetch. Okay, so within this pipeline stages, we have 4 instructions in here. So they can run pretty much 4 times faster because you run like a parallel processing. Okay, it's much faster, right? So that's a basic concept of pipelining. Pretty much these days, every processor, they have a pipelining. Now the question then, right now we have 4 pipeline stages. Okay? What if you increase the number of pipeline stages? Let's say not 4, but let's say 8 pipeline stages. Would it be better? Generally, yes, that's better. If you buy your Intel processor, right? And now you may want to read those small booklet, and then it gives you technical details. You possibly see 8 pipeline stages or 16. These days, Intel processor, they increase the pipeline stages a lot, like 8 or 16. Okay? In 8051, our processor, okay, it's like 30, 40 years old. They probably don't have it. But these days, every processor, they have a pipeline, this pipeline. Okay, so you need to remember this. Very basic, okay? Okay, so you want to remember this. We probably discuss this one later because there are some more details. Okay, what if you increase it and this is generally this is better because you run it 4 times faster, but it's not always. There's some problem about this one. We'll see those things later. Okay, so right now simply you can think that okay, there's a pipeline technique and this one is typically good because you can run many instructions per second much faster. Okay, so generally it's good. There's a concept called Endianness. Endianness. What is Endianness? Does someone know that? If you do a lot of C programming, then probably you know this. Endianness. Okay, sometimes it's very tricky to deal with Endianness, especially when you write a C program and that program has to run onto embedded system. Maybe in the PC, if you write a C program and Windows, always, probably you don't see this problem. But let's say when you write a C program and you run that in the DC washing machine or some kind of embedded system, or maybe automobile, okay? Those things, then you will always see this problem. So what is Endianness? Is this one. We have 2 different Endianness. Big Indian, little Indian. Okay? Big Indian, little Indian. Here's an example. Let's say, as I said, right, the address is always a byte address. Okay? Byte address. But in C function, let's say you write a program in your PC, and if you declare integer, then what's the size of integer? In PC, it's a 32-bit, right? If you declare like an int C, that's going to be 32-bit. Okay, 32-bit. 32-bit, you have a 4-byte, right? So let's say in your 32-bit, you have a value like 8, 9, A, B, C, D, E, F. This is an example, okay? So what I'm saying is this one. Let's say I write a C program, and in my C program, I declare int, and that's a 32-bit. And in my int, I have 89, A, B, C, D, E, F. This means hex, basically, right? So this is what I did, okay? I declare 32-bit container, and inside the 32-bit container, I initialize that with this value. Okay, this is what happened. What I did. Now let's understand what happened inside the memory. We have a memory like this, and memory has an address. Let's say this is a data memory, and inside the data memory, let's say this is where you have A. When you compile this one, right? The compiler will read this, and what the compiler does is that whenever the compiler look at this one, compiler will reserve this memory for A. Okay, make a container into the data memory. Okay, so that's what compiler does. So this one is A, and since this is 32-bit, 4-byte. So let's say you have 100H, 101, 102, 103. That's A, okay? This is an example, right? A is allocated into here. Now then, I write it as a 89, A, B, C, D, E, F. Okay? Then this value goes into here, right? This value will go into here. How does that go into here? That's the question. That's where we talk about Endianness. If this is a big Indian, then this value goes into memory as you read. You read like 89 AB. So 89 goes into here, which is the lowest memory. And the next memory is a 101, so that goes into AB, CD, EF. That's a big memory. So for us, it's natural, because I read it as 89, AB, CD, EF. So in the memory, it's basically the same order, 89, AB, CD, EF. It's the same order, so it's easier for us. Okay, I'm basically talking about what happened inside the memory. okay, inside the memory, the hardware. So that's big Indian. But there's another Indian called the little Indian. In little Indian, you have a same program, okay? I'm not talking about the program. C program, it's the same thing, okay? It's exactly like this. But when the compiler look at it, compiler knows that this processor is a big Indian or that processor is a little Indian. Whether big Indian or little Indian, it depends on the processor, okay? One processor, they use a big Indian. Another processor, they use a little Indian, okay? This is a processor dependent. In little Indian processor, they reverse the order, okay? 89 goes into this memory, A, B, C, D, E, F. That's what happened in the little Indian. So it's like a reverse order because I write it as 89 all the way to EF, but EF goes to the first memory. EF goes to the first memory, and CD, next memory. Okay, next one. That's a little Indian. That's what you see here. Okay, in the big Indian, the value goes into memory as the same order as you have, but in little Indian, it's a reverse way. You know the Intel processor, okay? The processor we are using, they use little Indian. Okay? Intel processor, they use little Indian. So right now, when you write a C program, you don't care. Okay? C program, you never worry about big Indian, little Indian. You never worry about. But you write a program like this, and you compile it in your Windows, right? And for some reason, if you look at how this value is written in the memory, then you will see this way. Okay? Which is actually reverse way. That's what exactly happened in your PC, in little Indian. Okay? Okay? So that's something very important when you do like embedded programming. Okay? Embedded system design. This is always an issue. Very important issue. But anyway, right now, at least you want to remember what it is. Okay, later, let's say you go to industry, you join Samsung and work on some of the system, then you always see this kind of thing. This word, you always see it. Okay, so remember that. Big Indian is a natural order, but little Indian is reverse order. And Intel processor, they use a little Indian. But some other processor, like ARM processor, there are many other processors, right? They use a big Indian. Okay, so some processor use big, some other processor use little Indian. There's a processor type called the CISC and RISC. Have some of you heard about this one? Yes. Yeah. Okay. What is it? Which one did you hear? RISC, CISC. Okay. So here's the thing. As you see here, CISC. What is CISC? Complex instruction set. RISC is a reduced instruction set. So what does it mean? Okay, this is what it means. Let's go back here. So as you see here, we have several stages happening in the microprocessor, right? Microprocessor fetch the instruction, and they have to do decode, right? What is the decode? What happened in the decode is that the microprocessor has these many instructions, okay? Generally, they have add, multiplication, store. There are so many instruction set, okay? And what decode does is that when they fetch the instruction, you want to compare which one it is, okay? You want to look at what instruction it is. So in the CISC processor, by the way, Intel, previous Intel processor, even these days, Intel processor, they have a CISC architecture. Okay, Intel processor, like traditionally, they prefer the CISC. And what this CISC does is that they have many instructions. like a complex instruction set, meaning that they have so many instructions. Okay? Even very complex instructions, they have all of them. Whereas in RISC processor, what they do is that they have a reduced instruction set. Basically means that they have only small number of instructions, only the basic ones. So here's an example. Let's say, let me compare these two. It's easier to understand. In the RISC processor, the only instruction you have is like addition and subtraction or load or store. That's it. Something like this, right? I'm giving you example, just an example, okay? So the RISC processor is like you only have a basic functions, addition, subtraction, load, store. Then, let's say you want to do multiplication. Let's say you want to do it, right? Multiplication. Then how can you do it? This one has no multiplication instruction. You only have addition, subtraction, things like that, right? Only the basic one. Then how can you do multiplication? You know, the multiplication can be calculated by additions, right? You put many additions, then you can still do the multiplication, right? That's what you need to do. Because in this case, you have no multiplication. I'm just giving you an example, right? You have no complex instructions. So if you want to do complex instruction, if you want to do complex operation, then you need to use some basic instructions. Put that together, okay? And only then you can run some complex instruction. That's reduces the risk. However, in CISC, they have an instruction like a multiplication. Okay? So if you want to do multiplication, then you can run one instruction, which is mult or something like this. Then this will do it for you. Okay? This has a more instruction, and there are some complex instruction already there. That's the difference. So sounds like this is better, right? CISC is better because the hardware has all those instructions already, right? So you can just call the instruction, then hardware will do the multiplication for you. So sounds like it's better, right? In fact, that's why actually Intel started to architect or design their processors using CISC, okay? But there are other companies like Sun Microsystems, and there are some other HP, and there are many other computer companies. They design their processors using RISC. Okay, Intel is probably one of the company they use CISC. So now let's see the difference. In this case, you have a lot of hardware instructions, so therefore it is a complex hardware because you need to have more hardware, right? You need more instructions, so therefore you need more hardware. So this is more hardware. And also, in this case, right, if you want to do multiplication, you simply call multiplication. So it's a compact program. Your program is compact. For us, it's easy, right? You can just call the multiplication, that's it. So the size of the program is small, but in RISC, what happened is hardware is simple because you only have a small set. Like you have addition, some small number of instruction, right? Hardware is simple, and your instruction sometimes is very long. Because if you want to do multiplication, then you have to put a lot of addition, right? That's how you do it. So it's a program size is big in this case. Sounds like CISC is good, but in fact, that's not the case. These days, okay, these days, a lot of microprocessor, they design it using RISC, okay? CISC, pretty much it's gone. I cannot say it's gone, but Intel processor, they started to architect their processor using CISC, and even now, they still do it, but pretty much they are trying to convert, trying to design their processor using RISC. Even Intel, they do it. So why is that? Sounds like this is better, but a lot of designers, they are trying to do it this way, RISC. Because of a higher power consumption, that's a good point. This one has a very high power consumption, simply because its hardware is complex. But that's one reason. And another reason is that, let's say we have so many different constructions. So many different instructions. Like I gave you example as a multiplication, but inside here, there are many other complex instructions. Maybe some division or any other things. But now let's guess. You have a lot of complex instructions, but in your program, how many times do you use that kind of complex instructions? So basic, like add, subtraction, you always use it. But some of the very complex instruction, maybe you use it very often. Maybe you use it like maybe once a day or something. It's very rare. Okay? You are not using it all the time. But since you have everything in here, you have a very big hardware, okay, and large power consumption. And another big problem is that in hardware, generally you have a big hardware, you cannot increase the clock speed. Okay? There is a certain limit on the clock speed. With a CISC processor, probably the processor cannot go beyond a certain gigahertz. Okay? You want to speed up. You want to speed up your processor, but this processor is too big. Okay? So the clock speed cannot go really fast. Okay? So we have a problem. So far it was good, but we have some problem. That's why the Intel, they are switching. And RISC actually is a very simple hardware. Very simple. So you can speed up. The clock speed can go very fast. Okay? So that's why, and the power consumption is also very low. Compared to this one, it's very low. So therefore, these days, this RISC is a better architecture. So a lot of processors, they prefer RISC these days. But as I said, if you look at the program, this one, you can have a simple program, but this one, your program can be a little bit large. Okay? Because in software, you have to use all the basic instructions to do calculation, complex calculation. You can see this picture in your book. Okay? This is from your book. This is a very basic connections. This shows you very basic connections between your processor and the memory. Okay? So here's the thing. This is our processor, 8051. You see here 8031, right? But basically the same thing. Only difference in 8031 is this one has no internal ROM. Okay? But all the other things are the same. We have a 8031. And inside here, you have a port 0 and port 1. There's a port 1, port 3, and here we have a port 2. Port 0, port 2. Okay? So in this example, right now, port 0 and port 2, port 0 is connected. This is a connection, right? This is connected to EPROM, which is instruction memory. And this port 0 is also connected to RAM, data memory. So we have an instruction memory here and data memory here. And this pin goes into both of them. Okay? That's what you see here. And this one, right? Port 2, it only connected to instruction memory. And also, it actually also both memory in here and also here, right? In the EPROM and this one. But this one also has a connected to the latch. Okay, that's what it shows. This port 0 is connected to the latch, connected to the EPROM, connected to the RAM. And this port 2 is connected to the instruction memory and also data memory. So now, what you want to do is that here, if you look at the port 2, it has A, right? It shows A, A8, A9, A13. So what is A? A means address. Okay, A means address. And if you look at the port 0 right here, right? Port 0, then you see that AD0, AD1, all the way to AD7. Okay? A means address, D means data. Okay? So that basically means that in port 0, every port, each port you have 8 pins. So in port 0, we have AD0 to AD7. So since these are in port 0, this is AD, which means that this can be used as address and also data. Okay, this port 0 can be used for both address and data. And port 2, this is only for address. Okay? Now then, you may want to ask a question. Data, we only use port 0, but address, we use port 0 and port 2. Why? Because remember that the data we use is 8-bit, but address space is 16-bit, right? So for address, you need 2 ports, because each port is 8-bit, but we have 16-bit address space, so you need 2 ports for address. But data, it's 8-bit, so you need only 1 port for data. That's one question, right? That's one thing. Another thing is that look at the port 0, right? Now the port 0 is used for both address and data. So how does it work? I mean, generally, right? Generally, forget this one, right? Generally, how things should work is this one. Okay, here's how things work. Generally, let's say you want to read some instructions from instruction memory, right? Then this microprocessor send out the address of that particular instruction, okay? Then this memory will return that value to the microprocessor, okay? So address value goes into the address line, and the actual value goes back with the data line. Same thing for when you access the data memory, the microprocessor will send address. Okay, I want to access that address. Okay, the address value go into address line, and the value on that address will be returned using data path. Okay, so you should have address path, data path separately, because address go first and then data return. You cannot use these two at the same line. Okay, address should go to address line, data should come with the data line. But in this case, look at here, this port 0 is used for both address and data. How does it work? Okay, that's something that you probably want to understand in 8051. So now, in order to understand this one, actually these days, right? These days, like right now, we are using 32-bit processors. Like Intel processor, sometimes they're 64 bits. So these days, pretty much the processor they use this way. Instruction path, the address path and data line, these two are separated. Okay? Only that way you send the address at the same time you get the data, right? You do the same thing, simultaneously. You do 2 things same time. Address goes here, data comes here, same time, right? Typically they do it. But look at this architecture, and 8051 was designed when? 30, 40 years ago. If you go to 30 to 40 years ago, then this processor was probably very expensive at the time. And if you want to, let's say, if you want to have address pin and also data pin separated, right? Then now what's the problem? You need so many pins. You have 16 for address, and you need 8 for data, right? So we need so many pins. Okay, what was the homework? Homework, we have we list up 40 pins of 8051, and right, and you want to describe the functionality of each pin. And at that time, like 34 years ago, they want to reduce the number of pins because that's very expensive. Okay, pins are very expensive, so they want to reduce the number of pins. So therefore, they come up to architecture like this. Okay, they want to make only 8 pin, and this 8 pin will be shared with the address and data. Okay, address and data. In order to reduce, they do it this way in order to reduce the number of pins. And we're using 8 pins. You use address and also data. Then now we have to think about that how we can share. Okay, we only have 8 pins, but we need to use that 8 pin for address. We also have to use that same 8 pin for data. So how can you share? That's the question, right? This is how you do it. That is why you need this latch. What is latch? You learn latch? Latch is another memory, like a flip-flop, right? And latch is a memory where you put some value into the latch, you write some value into the latch, okay? And then latch will hold the value, okay? Latch will hold it. Simply, that's it. Here's how things work. Look at here. This is time, okay? This is how time goes. First, what you do is that using this port 0 and port 2, you are sending out addresses. And your address is 16 bits, right? So using A0 to A7, this one, and using the A8 to A15, this one. So using port 0 and port 2, you are just sending address first. That's what it is. At this time, at this particular time, you are sending address 0 to A7, address 8 to A15 using port 0 and port 2. Same time, you want to send out ALE pulse. What is ALE? That ALE pulse is for latch. So you turn on latch at the same time. Why do you want to turn on the latch? Because you want to hold this value into the latch. Okay? So once you do this, right, look at here, at this time, you are sending out address for both ports, and the latch is on, so therefore A0 to A7, which is this value, goes into this memory, that memory, but that goes into also latch. But we turn on the latch, so the A0 to A7 value goes into latch. That's what happened right here. Okay? And on the next cycle, okay, next period, right, what happened is now then this value, lower 8-bit of address, already gone into the latch. So now, using this port, now you send out data. This port 2, you can just send address, no problem. But this one, you want to switch to the data. Okay, now, on the next time, right here, now we are sending data here. Okay, now we are sending data, but for address, this upper 8-bit address, you can still go using port 2, and lower 8-bit of address was already here in latch. So this one gives you the 8-bit, lower 8-bit of address, and this one, you have upper 8-bit of address. So 16-bit address is from here to the memory. And this line, you go to data. Okay? Right? So that's how things work in here. Okay? So the lower 8 bits, temporarily you put that value into the latch, and later here, using the port 0, you send out the data, and lower 8 bits of address is given by latch. Latch will instead of this CPU, latch will give the memory the 8-bit, lower 8-bit address. So that's how things work. And this one, right? This one is the enable signal. When you look at this one, right? You sometimes see bar here. Bar. What is bar? Huh? Complex conjugate? No, that's a. This basically means the active low. Active low. What is active low? Generally, right? Let's say I want to turn on this memory. Okay? Then this, you probably have some signal, right? So I want to turn on this memory. Then active high means that generally, normally it's a 0, but suddenly you turn on. You put the high, or 5 volt, something like that, right? Then this is active. That's active high. But active low means that normally we give a 5 volts normally. And if I want to active, right? If I want to turn on the memory, then I make it low. Then it's turned on. That's active low. So when you have a bar, that means active low. Okay? So generally these memory are active low. So therefore, look at here the read pulse and write pulse. These two. Okay? These two lines are active low. Okay? So normally this one you have a 5 volts like this. It's active. It's high. Okay? And if I want to write some value here, or if you want to read some value from RAM, only then you make it low. Okay? Then that's the signal. Okay, I want to read some value. Then you lower this signal. Or, okay, I want to write some value. Then at that point, you make it low. Okay, so this is a signal that you want to do. Whenever you want to read or write, you make it low. Same here, right? This one is for ROM. You have to make it low if you want to read it. Okay? Remember, this is ROM. So you can only read. Because this is read-only memory, right? So you only have a 1. But this is a data memory. Read-write, right? So therefore, you need 2 of them. Read-write. Okay? But if you want to read from EPROM, then you want to make it low. And if you want to read from RAM, you want to make it read low. If you want to write some value, you want to write low. That's what you see here. But you need to make sure that you want to read or write here. Okay? You should not do it here. Right? Because data is going into this time. Data to go into this time. Okay? So that's the 8051. So message here, the simple thing is that let's say there's a microprocessor. These days, as I said, we have separated address pin and data pin, right? In that case, you don't have to do this, right? You just send out the address. At the same time, you will get the data. Okay? So you don't need latch. Okay? Send out the address. I get the data, right? At the same time. You can do that, no problem. But in this case, address and data have to share this port. So therefore, this one first send out the address. Okay? And this part, 8-bit of address should go to latch. And latch will hold it. And then later, I send out the data. Okay? And at that time, the address has to be stored here, and that address is given to you. So from memory perspective, it still gets 8-bit data pin and 16-bit address pin. Okay? From the memory perspective. So it's like a time shifted. Okay? Yeah.
If I use active high with TSC and read or write, then are there any problems?
If you use active high, then you should do it the other way. I mean, it's a active high or active low. That's already defined in the chip. You cannot change it. It's not up to you. When you buy a memory, right, hardware, then hardware says that in the data sheet, it says that okay, this pin has to be active low. So you have to follow that. It's not your decision, right? Okay, so this is how you connect to the external memory. This is a little bit difficult, but okay, for this one, we'll do it next week. Okay.